Lecture 6, Interprocess Communication. When two or more processes would like to coordinate or exchange data in any way, the mechanism for doing so is referred to as interprocess communication, occasionally referred to as IPC, and that's the abbreviation for it. Now, if the process in question wants to share data with another process, well, the operating system has to provide facilities to make this possible. It's one of the many cases where we need the operating system to help us out, and in this case it is if you want to send some data from one process to another, that breaks down the isolation between processes that we would normally see, because there is exchange of information, there's exchange of data, and that has to be facilitated by the operating system. The motivations for interprocess communication are fairly obvious. If you look in textbooks, there's frequently all kinds of stuff about, here are some scenarios why you might possibly want interprocess communication. That seems to me to be kind of redundant. We don't have to spend 10 minutes and 15 slides going over why a process would ever want to communicate with another process. Every time you send an email, that's interprocess communication. In your own program, you can consider breaking a large task into smaller ones, allowing, say, multiple users to edit the same data, or for system modularity, or just about anything that you can think of. There are tons of great scenarios, and people having a phone call kind of example is also perfectly valid. So interprocess communication is actually a fairly substantial topic in this course. We are going to talk about it today, and we are going to cover several different mechanisms of interprocess communication. It actually stretches over multiple topics and therefore multiple videos. And we'll see as we go through the different kinds which ones are best for which scenarios and why you might choose one over the other. But before we enter into the first specific example, we're going to spend a little bit of time in this topic going over the general idea and the high-level overview of what is actually intended. So yeah, the motivations are obvious. I'm not going to belabor that point anymore. So before we proceed, I have to give you some definitions, painful as they are, brutally obvious as they are. When we are talking about interprocess communication, it is the transfer of data. Data is just information, ones and zeros, from one process to another. And the thing is that it is not necessarily the case that when data is being transferred, it's necessarily a large amount of text or anything like that. Sometimes information being passed is just notification that a thing has happened. And that may be sufficient. And the data being transferred is typically referred to as the message. The process that sends the message is the sender. The process receiving it is the receiver. I know, totally shocking. Whatever will we do? Thanks, Captain Obvious. Okay. Now, the thing about interprocess communication is it is totally indifferent to what the data looks like and how it is structured. So the processes involved have to have some agreement on what data a message should contain, as well as the way that the data is formatted. So you might agree that data should be transferred between this process A and that process B via XML. Okay, if you do that, the processes themselves have to be aware that the sender needs to format the outgoing message in XML, and the receiver will attempt to parse the incoming message in XML. That's fine, but how that agreement is made is outside the view of the operating system. The processes themselves are responsible for managing this, and therefore you have to know, it's published in the documentation for this program that it accepts XML input, and therefore we're going to write our program to generate XML output. That would be fine. If both things are within your same team, within your same company, you can just as easily decide, I want to use XML format for this purpose, and therefore we'll assume we'll do this. And each team member who works on the project knows interprocess communication always happens with XML. You could easily choose a different standard. JSON is quite popular, at least right now, but there could be any other format. Doesn't matter. You could invent your own format if you want. The operating system does not care. The operating system transfers data just as a chunk, and it pays no attention to what the contents are. If you wanted an analogy for that, you could think of it as being sort of like the postal service. When you put a letter in an envelope and you mail the envelope, the postal service does not care what language the contents of the letter are written in. You could write it in Japanese, doesn't matter. If the postal employees who don't speak Japanese need to collect the letter and deliver it, all they care about is what's on the outside, what's on the envelope. Is it properly addressed? Is there a stamp? Those are the things that matter. So the content is between the sender and the receiver. Now, sending and receiving could be either synchronous or asynchronous. And synchronous send means the sender sends the message and then is blocked from proceeding until the sender knows that the message has been received. That one is not super common, but it is entirely possible. Asynchronous send, the sender can post the message and carry on. That's like what you would imagine with letter mail. You just drop the letter in the mailbox and then you keep going. You don't have to stand at the mailbox until it's been collected and been delivered. Synchronous receive, the receiver is blocked until it receives a message. So if you want to collect a message, well, you have to sort of wait until a message is there before you are allowed to proceed. And asynchronous receive, if you check for a message that you want to receive and there's none, you just get told, sorry, no message is available, and you are allowed to continue executing. When I took an operating systems course that talked about this particular topic, the synchronous receive was explained to me by the professor as if you go to the mailbox and if there are no letters in the mailbox for you, then handcuffs spring out and clap onto your wrists, and then you are stuck and you have to wait by the mailbox until anybody sends you a letter. Okay, synchronous receive sounds dire when we talk about humans because, you much prefer the asynchronous receive. If there's no mail today, there's no mail today, and I would like to be able to, go on with my life. But synchronous receive does frequently make sense in the case of a program where it's waiting for some input. If there's no input right now, there's nothing to do, so we might as well wait at this point. We might as well be blocked at that point. In any case, your communication mechanism in its total will be viewed as one of these four combinations, depending on whether sending is synchronous and whether receiving is synchronous. So 3 of these are quite common. The last one is kind of strange. So synchronous send and synchronous receive, this is that the sender is blocked until the receiver collects the message, and the receiver waits for the message and it's blocked until it arrives. This requires basically that at the same moment the sender and receiver are exchanging the message. You could think of this as being a little bit like a phone call, in that both parties have to be on the line at the same time for a phone call to successfully work. Otherwise, it's not a phone call, it's voicemail. And that is a valid choice for communication. Synchronous send and asynchronous receive, this is the one that's actually uncommon. The sender is blocked when the message is sent, but the receiver will continue whether or not a message is available. Asynchronous send and synchronous receive, this is common for putting in requests to a server. As the client, I'm the sender, I want to send a request, and I can send it, and then I can just move on, and I'll get a response at some point later. And synchronous receive occurs on the server side, where it's just sitting around waiting for a message to say, hey, could you do this for me? And then it returns a result. The last version is asynchronous send and asynchronous receive. This is, if you want an analogy, more like text messages, which is I can send a text and then sort of go on doing whatever else I want to do. And if someone is expecting to receive a text, they can look at their phone and they see, oh, that person has texted me, or no, they haven't yet, and either of those is fine. It is also common in many of these scenarios to have, especially asynchronous ones, to have acknowledgement messages. We have received your request and we are working on it, or something to that effect, or we have finished your request and here is the result. If that's the case, you just reverse the labels. The receiver of the initial message is the sender of the acknowledgement. And a general paradigm for understanding interprocess communication is the producer-consumer problem. That is, you view the sender as the producer and the consumer is the receiver. And this will be generalized a little bit. We have a whole lecture coming up on the topic of the producer-consumer problem. But the producer creates something, and it's then somehow shared with the consumer, and the consumer does something with it. So if you request some data from the database, well, okay, you send in your request, fine, and the database might acknowledge that it has received your request. And then the roles could reverse a little bit. The database server is then producing the result, and then it is consumed by the shell, so it's printed out on the console, and it tells you the answer that you were looking for. The idea of producer-consumer is quite general and is applicable to lots of different client-server type situations, and therefore you may expect that there are lots of scenarios that you have worked with already where some sort of client-server model has already been put in place. Now, there are three approaches to how we will consider doing our interprocess communication, and all of these things are actually fairly common. It's really just a question of what makes the most sense for your needs. There's no single option that I would describe as being optimal in every situation. It will be up to you to decide what is appropriate for the system that you want to use. The first one that we want to talk about is shared memory. Okay. So I was struggling when I was trying to think of how could you visually represent all the mechanisms for interprocess communication that we just talked about, and the limiting one was obviously shared memory. So this eventually led me to conclude the only way to do this was actually the Mr. Spock way, because, well, how else will you represent shared memory but the Vulcan mind meld? So yeah, shared memory. Conceptually, the idea is fairly simple. That is, a region of memory is designated as being shared, and processes can read and write to that location just as if it's regular memory, regular read and write. There's some work for the operating system to get started. You have to actually tell it, I want a shared memory segment, and you have to actually join the shared memory segment. But once you do that, you're all set. You can just treat it as if it's regular memory, and accesses are no different than if you were reading and assigning other variables. So to do that, we need a little bit of setup, but once it's going, it's going. Why is the operating system involved in this? Well, normally a region of memory is associated with exactly one process. That would be its owner, and that process is allowed to read and write that memory, and other processes are not allowed to. If a process tries to access memory that does not belong to it, well, that process gets a segmentation fault, and that usually crashes the program, so that's undesirable, and you don't want that. If you want to designate memory as shared, you have to tell the operating system that it's okay, otherwise it doesn't do the right thing for what you need. And another reason why that matters is the operating system has to know that memory is being referenced by more than one process. As we know, if you end your program, any memory that has not been collected, that has not been freed, will eventually be cleaned up as a result of the program terminating. So if memory is shared, then the operating system knows that it can outlive the place where it was allocated. It can outlive the process where it was allocated, because you don't want strange behavior caused by the fact that if the process that created the shared memory is reaped, it's cleaned up, and that cleans up the memory, meaning that the second process is now trying to use an invalid region. So the previously shared region can't be considered free as long as another process is still using it, and actually we'll see in Unix that shared memory can survive while no process is currently actively using it, on the theory that you could just share this memory now and you don't know exactly when the other process is going to use it. but we need to manage that resource manually and do so correctly. Once an area of memory is shared, when either process attempts to access it, it's a normal memory access, and the kernel does not have to be involved. So here is a quite simple diagram of shared memory. This is one of those beautiful textbook diagrams that is somehow too perfect. Right? It is, process A and process B are exactly the same size, and the shared memory segment is exactly in the middle of them, and they both reference it. That's, of course, not really what it looks like. Processes have different amounts of memory, and they are located in different places in memory, and shared memory could be anywhere. It's not necessarily between them, so don't read too much into this diagram. It's a little too neat and tidy to represent what actually happens. Now, the thing about shared memory is it doesn't come with any form of coordination. So if the section is shared, you could have process A write some data in there, and then it's immediately overwritten by process B, and that isn't what you want. To prevent that, you need a system of coordination, and we'll see quite a bit about how to enforce those rules and get that coordination when we get to our topics about concurrency. We've already learned a little bit about how to do it when it's a parent and child process. Then we have one tool where we use wait for a parent process to wait for a child process, but that's really only the first one, and we need to learn a lot more before we can use things like shared memory efficiently. The file system. That's the second kind of interprocess communication that we want to talk about. In this case, I'm referring to the little plastic squares that Spock is holding in his hands. In one of those things that dates the original Star Trek to the 1960s is that there was an expectation that things would still be stored on tapes. They refer to these little cards as tapes, and that there are physical storage media at all. It seems sort of silly to us now, but hey, the future we imagine is just an extrapolation of the present, and is maybe not necessarily where we're actually going. But it is kind of amusing to think that they refer to these as record tapes. But sure, physical media are dying, but why not? They could make a resurgence in the hipster 23rd century. Now, the goal of using files for interprocess communication is, to make this a little bit more persistent. Unlike shared memory, messages that are stored in the file system will survive a system reboot or a crash of the whole operating system. Power goes out, anything like that. So that's fine. If it's shared memory, obviously it only works for as long as the system is up, and it allows things to be totally asynchronous, and we can just pick up those files anytime, even weeks later, even after a reboot, if that's okay. This can be used if the sender and receiver really know nothing about one another. If there's no mechanism for them to communicate directly, they can communicate indirectly via files. This method also might have been what you would have come up with if I said, can you think of a way, before we introduce the topic, for two processes to communicate? You might have said, just sort of off the cuff, not knowing any other methods, that, one could write a file and the other one could read that file, and that would work. And you would be correct. It does work. That is a valid option. It is a way to actually exchange data. To make that happen, what would you do? Well, the producer would write to a file in some agreed upon location. The consumer would then read the file from that same location. You still have to ask the operating system to get involved because file writes and reads are I/O operations and they are managed by the operating system, as well as there are permissions associated with who is allowed to read a file and who is allowed to write into this directory and that sort of thing. So you're not getting away from having the operating system be involved. It just looks a little bit different than we are imagining it looks when we talk about shared memory. If one file is being used, there is potentially a slight problem of coordination, which is who's writing right now and who's reading right now. You can get around that if you have multiple files with unique IDs. that a file is written, and then when there's a next chunk of data, it gets written into a new file. This example on here dates back many years to when I was a co-op student on a work term, and a producer generated some XML data, and it would write a file into a designated import directory. The consumer program would periodically scan this directory and import those files as their input. In this case, because one process was doing the writing and another was doing reading, there was no possibility that one process would overwrite the data of another. And if the sender always chooses distinct file names, increment a counter, add the current timestamp, something like that, we don't risk overwriting an older message if a second message is created before the first one is picked up. We'll see later on that sometimes we actually want to overwrite older messages. That might actually make sense for our scenario, but usually we don't. Spock to Enterprise. The next kind and third and final kind, really, of interprocess communication that we want to talk about is message passing. And message passing is more or less exactly what it sounds like. It is the idea that we are going to give a message to the operating system and ask that it be delivered to a recipient. And in that sense, it does resemble a little bit a postal system kind of view of the world, or email view of the world if you prefer, where you create a message, you address it accordingly, and you send it off, and you expect that it will be received because you expect the delivery mechanism to be at least somewhat reliable. So, yeah, message passing is a service provided by the operating system, and the sender is responsible for creating the message and giving it to the operating system with some information about how to deliver it. There are, of course, two basic operations. There is the idea of sending and receiving, and messages are allowed to be of either fixed or variable size. So our experience with email or postal mail or what have you should tell you that what you actually need to do to get a message delivered successfully is you have to say where it should go. And under the form of communication called direct communication, every process has to explicitly name the recipient or the sender of the communication. So process with the process ID of 1234 says, I want to send a message to process 5678 under direct communication, and process 5678 says, again under direct communication, I want to receive a message from process 1234. That's not super flexible. It does require us, of course, to know some identifier for the other processes, and that can work if we have something like a parent-child relationship. Well, the parent knows the ID of the child, so that makes it relatively easy to send messages to the child in this manner, but it's a lot harder for the child to get messages back to the parent, isn't it? Because the child doesn't by default know the process ID of the parent. It's not returned by fork, so you'd have to work around that somehow. Maybe putting in the message saying, this is my identifier. But how would you receive from that identifier if you don't know in advance what it is? So we can also use a form of indirect communication. And indirect communication is somewhat better. We will imagine that we will prefer to use indirect communication whenever it is an option. But for now, we'll just start with direct communication using signals. We got into the topic of interprocess communication when we talked about using them to kill your program with Control-C or using kill command or anything like that. And it really only makes sense at this point to start with signals when we talk about interprocess communication. So as previously introduced, it's really just an interrupt with a specified ID. They don't really contain a message within them, so they are somewhat limited. It's a little bit like pagers work, if you can imagine a pager, strange as those are to think about, doctors still use them. If you page somebody, you call a phone number, but you're paging someone and their pager vibrates, and really the only information that they get is who is the number who paged them. It sort of prompts you to, I should call that number back. And it's like a little bit a text message, except the body is always blank. You just see you have a message from this number. It is a technology that should be obsolete, yet somehow isn't. But when a doctor who is a medical resident gets paged, they are woken up in the middle of the night, and the poor sleep-deprived, overworked resident is alerted and has to react appropriately to the situation. They make a decision about what to do. They might need to give advice about what medication should be provided or transfer the patient or something, and then they can go back to whatever else they were doing before being paged, probably attempting unsuccessfully to sleep. Life of a medical resident is really not very much fun, at least as far as I am able to understand it. It does apparently get better once you stop being a resident and you become a staff, but that seems to medical residents like it's forever in the future. Okay. Now, the fact that the signal contains no message is a limitation, and it means that signals are not great for every possible scenario. However, there are lots of things where we can just use a signal because all we need is an indication that something happened. If you hear the fire alarm in a building, you don't need accompanying a voice announcement that says, "This indicates a fire alarm, please calmly exit the building." Why not? Well, I mean, hopefully, you have previously been informed of, this is what a fire alarm sounds like, and when a fire alarm occurs, it means you need to exit the building. And really the same is true for signals. You need to know what to listen for, as well as what is supposed to happen if you're going to react accordingly. So if you know that when I receive this signal, it means do this, you've decided on that in advance, and that's fine. That's how signals work. And the same is true with the fire alarm. You are prepared, probably dating all the way back to elementary school. You have been trained. This is what happens when there is a fire alarm, and this is how you should react. The appropriate header that you want to include in your program for working with signals programmatically is signal.h. This contains not only our function signatures that we need, and the definitions thereof, but it also contains definitions to let you write things like sigkill instead of having to put an explicit magic number integer 9 in your program if you wanted to send sigkill. If you recall from the previous talk about signals, there's a little table that says, these are the valid signals for your system. Obviously, that wasn't an exhaustive list, but you might remember that some of them had different values. So is it 17, is it 18, is it 20? There's not always 100% agreement what different implementations about higher signal numbers mean. Therefore, it is probably for the best if you use the name representation, where you use sig child, written all in capital letters, because that abstracts away the fact that on one system it's implemented as being 17 and on another it's implemented as being 20. Either is fine. It's whatever is correct on your system, and using the names just saves you from having to change that. Okay. There are two functions that are used to send a signal programmatically. We know how to send a signal on the command line using the kill command, and the two functions are kill and raise. Both return 0 if they were successful and -1 if they were unsuccessful. They, as is very common, have integer return types. The only meaningful difference between kill and raise is that raise doesn't take a process ID, so it does the same thing as kill, but it sends the signal to the current process. We're sending ourselves a message as opposed to sending it to an arbitrary process. But yeah, with the kill function, you can specify which process ID, so who is the recipient. That does make it direct addressing. We have to say, specifically, I want to send a kill command to kill signal to this process. And then the signal number specifies what signal we're actually sending. So you can send 9 if you want to send sigkill. You can type sigkill as is recommended. You could send whatever signal is appropriate for the scenario that you want. Okay, so we need to know the process ID of the recipient. If there's a parent-child relationship and the parent is sending a signal to the child, that's easy. We know how to do that because fork returned a value that told us the process ID of the child, so we got everything we need there. If, however, there is no such relationship, it gets a little bit more difficult. What do we do? Well, there are a number of conventions and strategies for this, but one thing that servers sometimes do is they register themselves. They write down their process ID in a location where they know that other processes could find it if they wanted to look. So MySQL database server puts its process ID in the file /var/run/mysqld/mysqld.pid. And the content of that file is just the process ID number of its process. So when it starts up, it says, I'm going to note down in this location, I'm going to say my process ID is 1494, and I'm going to do that by writing it in this file. If you know that, and then your intention is to communicate with MySQL, you just check this file and it will tell you, hey, this is my process ID. Any other communication method would work. However, we get the value of a process ID from the recipient to the sender. That's fine. You can choose whatever mechanism makes sense. The kill function does a number of different things depending on its first argument, and you can do some weird things with it. We're not going to focus on it, but I just include it here for completeness. But if PID is greater than 0, that sends the signal to the process specifically that you named. If PID is equal to 0, it sends the signal to all processes in the same group as the caller, so my current group. -1 is broadcast. I'm hard-pressed to think of a good scenario for this, but you could send the signal to all processes, at least all the ones for which you have permission to send a signal, except init and yourself. And PID less than -1 is send the signal to all processes whose process group ID is equal to the absolute value of PID. Are the details of that important? No. We care mostly about sending for process ID greater than 0, but just for completeness, I thought it necessary to mention this. You can also invoke the kill function with a 0 argument for the signal. That doesn't actually correspond to any signal that we would find in the signal table. That refers to the null signal. It doesn't actually send any signal. It would just actually check if the recipient process exists. If it doesn't, there is an error no value that is set, an error number that tells you it no longer exists. And this isn't actually super useful for two reasons. Number one, the process might exit between the time that you check for its existence and the time that you do something with that information. So you might send the null signal now and determine, does the MySQL server process still exist? And it will tell you yes. And then sometime later you want to send a SIGINT to MySQL. Well, in the meantime, MySQL might have exited. And that could happen actually no matter how short the window is between the time when you send the null signal and when you send the SIGINT. And the other thing is that process IDs are only relatively unique. That is, that process IDs can eventually be reused after they stop being used. So MySQL might have had this process ID of 1494, and it exited, and at some later time, another process that's running has been assigned that ID of 1494. So in that case, you might send a message to a process which is not the one that you thought you were sending it to. That's bad. So you should be quite careful about that. The null signal does have some functionality in determining whether a particular process exists, but its utility is quite limited. Now, one of the things that's worth noting is that a process can only deal with a signal when it's running. So things may not happen instantly. A signal is generated by something, by either an error in your program or by the kill command on the command line or by calling the kill function within a program. And a signal is generated and is delivered with some delay, small though it may be, to the recipient. And during the time between generation and delivery, we say that the signal is pending. And that just means that there is a signal that is going to be delivered as soon as the signal can actually be delivered. And the pending signal is typically delivered at the first opportunity, which might be immediately. If the current process that is executing is the one that is supposed to receive the signal, then it will get it straight away. But if that process is blocked right now, it won't get the signal until it gets unblocked, maybe, and that's okay. You just have to remember that it's not instant. A signal can be sent, but it can also be ignored. You can also choose to take no action, as is shown in this rather awkward conversation. So I mentioned previously this concept that you can block signals or you can ignore them, and now we can go into some detail about it. So for most signals, you can just choose to refuse to listen. This is slightly different from ignoring them. In ignoring them, you receive the signal and you say, yes, I received your signal and I choose to take no action. But blocking is somewhat conceptually different. Blocking is that I'm not going to accept a signal right now, and it means that a signal that has been sent that is being blocked is just pending until such time as that signal is unblocked. And you can block any signal other than sigkill and sigstop, because again, those are the terminator ones. They cannot be stopped, they can't be argued with, can't be bargained with, can't be reasoned with, and they will not stop until your process is dead. Now, when a signal is blocked, it remains pending until such time as you unblock it, and that implies that blocking is supposed to be temporary. Yes, a badly behaved program could ignore things indefinitely. You're not supposed to do that, but nobody could stop you, really. So it's up to you to be polite to other processes in the system. And signals have a default action, and the default action matters quite a bit. The action is referred to as the disposition of the signal. If you don't explicitly change what happens, you get the default, which is what's in the table, but we can actually change it. And there are effectively three options for what we could do when we're going to handle a signal, when we want to override the default. So option 1 is ignore it, option 2 is run a signal handler, and option 3 is restore the default option. So ignore it is straightforward and doesn't really require much explanation. Run a signal handler. This is take some action when the signal occurs. You can very easily simulate option 1 by just having a signal handler that does nothing for option 2. And option 3 is used to undo an earlier change. So if you said, I want to ignore the signal using option 1, and then at some later time you want to undo it, then that's what you can do with option 3. Our intention is to focus on option 2, the run a signal handler option in this topic, because it is the most interesting and is the most flexible, and in principle you could use it to simulate the other choices. Okay. If we decide to register a signal handler, the function to do that is kind of ugly. What's going on here? It is difficult to read. The good news is that using it in practice is much easier than it looks like here. What we actually have here that makes this somewhat complicated is we have a function pointer notation. And function pointers are a key aspect of C programming that for a long time just did not make an appearance in Java and have been frowned upon a little bit in some cases, but now they are in vogue again. So that's good to see because they're actually very useful. But what we are saying when we want to do this is we want to register for a given signal this handler. Okay. It will make more sense when we actually see an example, but we are saying when signal X occurs, run function foo. So in our definition, signo, that's the signal number to watch for. So if we want to catch sigint, we would provide sigint here. And handler is the name of a function to run to handle the signal. And the function has to meet the following definition. It has to have return type void, and it can be named anything you want, and it has to have one parameter of type int. So the sample signal handler that's shown down here, void sig handler, takes an argument int signal num. This is a valid signal handler, and we could use the name sig handler as the second argument to the signal function. And as long as our function name conforms to the expectation of the function pointer, that is, it has return type void, and it has one parameter of type int, then that's okay. There are restrictions on the function signature. If this sig handler function had a different number of arguments, or it had a different return type, or even a different type of argument, it would not be valid to provide here. So one of the other reasons why this void signal definition is so messy is it returns a pointer to the old handler if one existed. If you were just setting it in the straightforward way, it would look a little less like, why are there so many parentheses, help. So that's why it is the way that it is. We'll see in a later example how to actually use this, and it will make a lot more sense. So your signal handler workflow looks like this. Your program is executing, and here in the main program box, and there's some flow of execution. At some point, instruction M is completed and a signal is delivered. At that point, the kernel invokes the signal handler on behalf of the process. The code of the signal handler is executed, and then we return, and we resume at the point of original execution. And so this is how our signal handler will actually handle the incoming signal. We just pause what was going on in the main program, we jump over to the code of the signal handler, we execute that, and then once it's done executing, we resume right after where we left off. To illustrate how simple signal handler actually is when it comes down to it, in spite of the very complicated looking definition of the signal function, let's consider this super brief code example. Now, as before, we have to include signal.h here, just to make sure that we have all our definitions in a row. And I've written a signal handler function here that begins on line 7, and it is just called handle it, and it conforms to what is required by the specification. That is, it has return type void, and it has one int parameter called signal num. I can call the function anything I want. I can name the parameters anything I want. Those don't matter. All that matters is the return type is correct and the arguments are correct. And our program will do the following. So the first thing that happens when we start up main is we register the signal handler. We register the signal handler, say signal is the function for that, sigint is the signal that we want to register it for, and the function that we want to run when sigint is observed is called handle it. And the compiler will be able to figure that out because I've defined handle it above main, so no need for a function prototype of it, and that will actually do what we need it to do. Then we have an infinite while loop here. While quit is 0, don't do anything, just empty loop, spin, and when the signal handler occurs, well, it will set quit to be 1. That will break us out of the loop, and then we will have a printf statement here that says time to die, which tells us that actually things went as expected. So you'll notice also attached to the int quit variable up on line 5 is the keyword volatile. Volatile is one of those things where it's quite possible to use wrong and get bad behavior, but volatile is used in this instance to tell the compiler not to optimize away the comparison here at line 13. Without that, the compiler might conclude that quit is always going to be 0, and therefore it will just replace this loop with while true, and then our program doesn't work as expected because we don't change anything when we set quit to be 1. That change is not observed anywhere. So for that reason, I've used volatile. It is frequently the case that you want to use volatile for something that is changed in a signal handler to make it clear to the compiler that this could change unexpectedly. But okay, signal looks pretty straightforward. We just say for this signal, take this action, run this function. And if you're wondering why the signal handler function has a signal number here, it's because you can reuse the same function for multiple signals, but you can have them be a little bit different. So when handleIt runs, it gets signal number of sigint, because it's the only one we registered it for, but we could have registered it also for sig hangup. And if we did that when handleIt is invoked, then the function can see when it's called what signal it is responding to. That might be helpful if you want to just have very similar handlers so that they don't have to be copy and pasted, or they could do the same thing with slight differences, but that's okay. So let's actually run this and see if it does what it is supposed to do. Okay, and we should expect it is spinning, and when I press Control-C, send sigint, it's time to die. If you wanted a little more demonstration that actually something is happening here, we can do that as well. Add a printf here, and then sleep. Sleep just puts the current thread or process to sleep for a bit, so it's just effectively a wait. And do nothing. We'll compile it again. Okay. Here's one of the things that I've mentioned previously but haven't shown. I got warning implicit declaration of function sleep because I haven't actually included the correct header to deal with that. Now you can Google this, of course, to look it up. For the moment, we could ignore this error because it's only a warning and therefore it doesn't prevent compilation of the program, but you want to fix those warnings, so we should do that. And if you Google it, you will find that sleep is defined in the UNIX standard header. And if we compile it again, the warning is gone. So yeah, if we run the program now, once a second it prints out waiting until such time as I press Control-C to send sigint, and then we get time to die. You get the same behavior, incidentally, if instead of using the Control-C, you would send sigint from another program that knew the process ID of this executable, or if I use the kill command on the command line, we would get the same behavior. So that's the simple version of how to write a signal handler. You can, of course, do more things other than just set quit is assigned 1 in your signal handler, but there are some rules about what you are allowed to do in a signal handler, and we have to be a little bit careful. Yes, in fact, the content of the signal handler is restricted. The handler deals with an interrupt, and it can run between any two arbitrary instructions, and it's therefore very important to make sure that the signal handler does not mess anything up. For example, if the signal handler runs in the middle of a memory allocation and the signal handler itself does a memory allocation, that could actually put memory management into an invalid state, and that's not okay. We can only use functions that are reentrant. There is a formal definition of reentrant that is somewhat complicated, but the simple language definition of this is it's a function that can be interrupted during execution, have another complete call to that same function execute, and then the original call of it can resume, and everything turns out okay. There are whole tables about what functions are safe to invoke from within a signal handler. More generally, if you want to check the documentation, you're looking for a designation async signal safe. If the function has that definition, it is allowed to call it in a signal handler. If not, you should be careful, and you probably shouldn't. In particular, common functions to avoid doing in signal handlers are printf, malloc, free, and anything that could possibly block the process, so read of a file, trying to access some external resource. You don't want to do that. That's why the handler in the example we just did doesn't print anything to the console, because printf is not async signal safe, and you shouldn't do that. Now, if you want to block signals, or actually even just ask the system about what is the current state of which signals are blocked, there is a function for this, and it is sigproc_mask. And sigproc_mask takes 3 arguments. It says how, the set of signals, the new one, and the set of old ones. So the how argument is used to specify what operation do we want to do. Do we want to block a signal? Do we want to unblock one? Or do we want to overwrite all the current values with sig set mask? If we set how to be block, then the sig block, then the signals that are in the set of the second argument will be added to the block list. If how means unblock, then the signals in the set are removed from the block list, and set mask says replace the block list with the set that is provided as the second argument. If you provide a third argument, a pointer to a sig set t, that will be updated with the old value, so the previous state, so you can save that for later if you need it, or if you want to restore it. You could also just provide null as an argument, in which case you don't get the old values because maybe you don't care. Now, a sig set t is a structure, and it is a structure that we don't have any information about its implementation. We don't know what the contents are like, and we actually shouldn't know and shouldn't care. All that we care about is it's a set, you can put signals in it, you can take signals out of it, and it is going to work as expected. For that reason, we don't know really how to interpret it. We don't have to assign things. It's not really an array. What we do is we use the helper functions that are associated with the set to actually make this work. And it's the responsibility of the implementers of these functions to worry about how to actually populate the set correctly. So sig empty set function, first one here, initializes an empty sig set t, because obviously we don't know how to initialize one if we don't know what its contents are like. So we create a set, let's say we malloc it, and then we provide an argument to sig empty set of that newly malloced sig set t, and it will be initialized to empty. There is add, which adds a specific signal to a given set. So given this set and sigint, we're adding sigint to that set. Sig fill set adds all valid signals to the set, so all the ones that you are allowed to add will be added. Sig delete set removes a specified signal from the set if it was in there, and sig is member returns 1 if it's true and 0 if it's false, so that the provided signal is a member of the provided set. So let's actually look at an example. This is a snippet of how you would do this. We're going to declare a sig set. This one is stack allocated, and we'll have a previous sig set, so we can store the previous values if we are going to restore them later, which is the case here. We will initialize our signal set to be empty with sig empty set, and because a pointer is expected and we have a local stack allocated sig set, we need to use the address of operator. This creates an empty set, and it is now initialized. Sig add set, we're adding to the set sigint. Okay, so then we're going to use sigproc_mask and say add to the set of blocked signals. I want to add all the ones that are in the set, that is only sigint, and we're going to save the old configuration in the previous sig set t. Then we have some block of code, not shown here, which is just where sigint is blocked in this section. So while we're doing this, if a sigint occurs, the sigint remains pending. It can't be delivered until such time as sigint is no longer blocked. And one of the things to watch out for actually is it is operating system dependent. If the same signal is sent more than once while that signal is blocked, it might be delivered only once, depending on your operating system implementation. But if it's sigint, we probably expect it was meant to be delivered only once anyway, so it might be okay. But in this section, however long it is, if a sigint occurs, it is pending until such time as sigint is unblocked, and that happens here with the second call to sigproc_mask. We're now going to replace the blocking mask with the previous one, and we don't need to update any, what was the state before the sigproc mask second call, and we just put things back the way they were. We're restoring the previous mask, and now SIGINT is unblocked again, and if there was one pending, it will be delivered. If not, it isn't. That wouldn't be a problem. There is also one more thing you can do with a signal handler, which kind of just ignores it, but does a little bit of waiting, and it is the pause function. If you want to pause your program until you get a signal, well, pause will do this. This always returns -1. It just suspends your program until a signal handler runs. It can be useful if you want to wait until a signal has arrived before you continue doing something, as opposed to just having a loop where you're waiting. As in the example that we just saw, having that loop is maybe not ideal. Maybe you would prefer to pause instead, and then you will be unpaused when the signal handler has run. This can be quite useful if you really did need to wait for something. Pass your message. Okay, the picture here represents our current state. In that we've learned how to use a signal to pass a message, as long as you know the recipient ID. And it doesn't really contain any message at all. All you know is you got something. So like the unhappy person in the green shirt here, you know you got a message, but there's no text, so it maybe wasn't as helpful as you were thinking it would be. And we'll circle back now to address the situation of direct addressing, and to deal with that, what we're actually interested in is indirect communication, where messages are sent to a mailbox, and a mailbox is really just a message queue of some sort. A queue is owned by the operating system, so it is independent of any particular process, and it is persistent. And this is more like what happens, when you send a letter, you mail a letter to the university. That's fine if it's just addressed to the registrar's office. It's not important who specifically at the registrar's office gets it, and if someone who's working at the registrar's office retires and then a new person starts working there, they can continue to pick up the registrar's office mail. It's not really a big deal. You don't have to name that specific person. So we would actually like indirect communication where you send messages to mailboxes, and that really helps. And Unix gives you that, and the Unix term for this is a message queue. The total number of queues that are available and the maximum number of messages, as well as the maximum size of each message, are all implementation specific. That is, depending on what operating system you're using and how it's configured, those numbers will vary. I wish I could give you an exact number and I could say, oh, well, it's typically this or it's usually that. There's no good numbers for that you can rely on. So you have to consider the possibility of limitations. In a real implementation, you basically have 3 choices of what do you do if the queue is full. Number 1, you could wait for space to be available, so you just block the sender until such time as there is space in the mailbox for the recipient. That could be a while. Number 2, you could overwrite older messages, and sometimes that is what you want. If this is weather data that's being reported, the weather from an hour ago is not as important as the weather from 10 minutes ago, is not as important as the weather from now. So overwriting older data is fine. Third option, discard the current message. The older messages are more important, and you just leave the old ones where they are. And that's what happens, if someone's voicemail box is full, you get told, I'm sorry, but you can't leave a voicemail because the voicemail box of this number is full, and therefore you can't leave a message. Your current message, whatever you want it to say, has to be discarded. And we're going to take some time to actually look at Unix message passing and actually work out how to do it, how to send a message and see how that works. It is fairly complex, so there's a lot of things that we need to do to make this work. The first step in message passing is to get a key that identifies a specific queue. Keys are just integer values, and we would like them to be unique or at least close to it. One method to make a determination about what the key is there is a file to key function found in the header sys/ipc.h, and it returns a key. It's a key type, but is really just basically an integer. And this file f2k, file to key, takes a path name, so it's a file, and then a project number. So two processes that don't know anything about each other could agree on what their IPC key is by agreeing we're going to look at this file name, so /etc/something, and a project number of 42. And if two processes call file to key with the same arguments, they will produce the same key. The file does have to exist, and it does work. And as long as we agree in advance what these are going to be, then there's no problem. This file could be reused by multiple systems or multiple processes that want to use it. That's why the project number allows you to have multiple IPC objects based off the same file. There is a risk of duplicate numbers, in which case messages are getting sent to the wrong queues, or sent to a queue that you thought was not shared, but it is shared. The risk is small, so it's usually considered acceptable. Another way that you can get a key is using a constant IPC private. And if we give in this constant where a key type is expected instead of generating a key with the file to key function, if we give in this IPC private constant, then a guaranteed unique key will be returned. And this is ideal when we have a parent and child relationship, and therefore the parent and child can use this IPC private before, well, the parent uses it before fork, and the child will then know the result, and there's no problem. Now, regardless of how we generate the key, we get the queue with this function message get, or MSG get. It's not the same thing as dequeuing a message, but this is how we access the queue. And it will take the following arguments: key and flag. The key is either something that we have generated using file to key, or it is IPC private, depending on which route we have chosen. Flags is Unix permissions, and permissions follow the Unix standards, so if you want it to be a read and write by the owner, 0600, something like that, and you will combine them with IPC create if you need to create the queue, and possibly combine with IPC exclusive, which says fail at trying to create the queue if the queue already exists. And they are combined using the bitwise OR operator. We'll see that when we get into the actual example. And the return value, the integer return value here, is the queue ID. That ID is going to be used for the actual communication that we want to carry out. Okay, now unlike in a lot of other contexts, the message has a defined structure. It is a struct message buff, and it has a long message type, and then it has character mtext, and it is an array of size 1. What is this? A message for ants? Well, yes, but actually no. The definition of this is not as dire as it sounds. It looks like a message can be only one character at a time, but that's not true. What it means is whatever message type you define has to have the first part be a long value, this long M type, and it has to always be a positive number, and then you can have anything you want as the body. So in this silly pirate-themed example, a pirate info struct is defined as the body of the message, and a pirate has a name and a ship type and a notoriety value and how cruel they are and how much money they have accumulated through their piracy. You are allowed to define whatever you want as the body of the message, as long as it conforms to this rule that the first type has to be a long, and long is always going to be a positive number that specifies a message type. Then to send a message, send is kind of straightforward. It is going to take the queue ID, so send to the following queue. the following message, we have a pointer to the message to send. It is a void pointer, meaning you can define whatever type you want as being the data that you're going to send. It has a size, that is the length of the message. That's how we know how many bytes we should actually read from the source when we're sending it. And flag is either 0 for blocking or IPC no wait for non-blocking. If the queue is full, then IPC no wait option means we will return with an error telling you that the queue is full. For simple implementation, we're fine with just 0 and having a blocking send. But if you prefer a non-blocking send, then you can try this with IPC no wait constant as the last argument. Okay. And then there is receive, and receive is ever so slightly more complicated than sending. Sending just required you to specify this is the queue, this is the message, this is the size, and are we willing to get blocked? Receive gives you a little bit more. Receive says we're going to get a message from this specific queue. We're specifying a destination, that is where we are expecting the data to be copied to. We're copying the message from the queue to our destination. The size, this is the number of bytes. And then flag is used for blocking or IPC no waits or return with error if the queue is empty. And the second last argument type allows you to specify what kind of message you want. So this is why there is this long M-type requirement here, is that you can send lots of different messages into the same queue, but when you are dequeuing, you can specify, I want a particular kind of message, or at least a particular category of message. And there are 3 options. If you specify type is 0, it returns the first message on the queue of any type. So that says, I don't care what the type is, that's fine. If you specify type as being greater than 0 when receiving, it means you want the first message on the queue that has that type. So if I'm interested in a message of type 4, then I will get the first message, if there is one, on the queue of type 4. And if the type is less than 0, so you said, -10 for the type, it returns the first message on the queue whose type is the smallest value less than or equal to the absolute value of type. So that means if there is a message of type 1, it will return 1. If not, it will go to 2. Maybe there is no such message up till type 9, and then it will return you the first message of type 9. So receiving is a little bit more complicated. It's made somewhat simpler if you just say, I'll take the first message of any type, but the type is actually somewhat useful and gives you some information about what kind of message you actually got. Okay, when we are done with the message queue, it is important to remember to clean it up. Just remember to destroy it when we're finished. And the function for this is message control, MSGCTL. It is much more flexible than just destroying, but we're only going to use it for the purpose of destroying. And this is taking 3 arguments, message queue ID, the queue ID that we got back from message get. The command to destroy is always going to be IPC RMID, so get rid of it, and then we will just provide null for the last argument. Again, message control is more flexible. It can do lots of things. We're only interested in using it for destroying the queue when we're finished. It is important to remember that this immediately deletes the queue, destroys it, and throws away any of the messages in the queue. Send copies the data into the queue, so makes a copy of the data and sends it in. Receive takes a copy of the data, moves it out of the queue, and we need that data to continue to exist if you've sent some messages that have not yet been received that you are expecting to receive. So you have to be careful about when you choose to destroy the queue. You should do so only when you're absolutely sure that you are done with all of the things that are inside. And we're going to take a quick look at an example. It's shown here on the slide, but it's better if we look at it actually in the editor and we can run it. Okay, we've had to include a couple more headers here, in particular the IPC header, as well as some things for types and message queue, but that's OK. We've got our definition of the type of message here. In this case, I've made it a very simple one. It is conforming to our standard that we have to meet, in that the first parameter is a long value, and I've called it M-type, but it doesn't have to be called that. The payload of this, the body of it, is just an integer int data. Again, I could make it anything I want, anything I need, and that will do just fine. Now, in main, we're going to define our, we're going to create our queue. So we call message get. And we don't need to use a file in this case. We're going to use IPC private for our key. And for the flags, we're setting the read and write flag for everybody and for the group and for the owner, just as we would with a file. And we're combining it using the bitwise OR operator with IPC create. So that means create me a new queue with flags 0666, that is, with everybody able to read and write it. And then we call fork here on line 16. Now, the thing is that because we called message get before fork, both the parent and the child have message queue ID defined, and therefore we don't have to work out, oh, we're going to use this file and we're going to try to communicate it from one to the other. We've done that already in advance, because we knew we were going to create a parent and child process relationship. It's actually quite easy to just do the setup in advance. And that's what we want to do. We want to do it before fork. If this message get happened after fork, then the parent and child would get different queues, and we do not want that. Then they would not be able to communicate as expected. So if the process ID is greater than 0, the parent process declares a message M. It sets the message type to be 42, and it says the data is 252. And then it sends the message into the queue, message queue ID, by address of, so take the address of the struct message that we have declared, and the size is determined using the size of operator, again saving you from working out what the actual size is directly, and 0 for the flag, so we're comfortable with getting blocked if we need. Once that's done, the parent process will exit. The child process declares also a struct that it's going to receive, and it will attempt to receive here this message queue ID from the message queue ID into message M2. Again, the size of this message, and we're going to attempt to receive only a message of type 42. It so happens, of course, that's the kind of message that we sent, so that works. We will expect that we receive a message. We could also here in this parameter here, 42, specify a message type of 0, in which case we would take any message, whatever happens to be available. Once that's done, this is a blocking receive. So only once that's done can we go on to the next line, and we will printf here the data that we received. And once that has finished, then we will use message control to destroy the message queue because we're finished with it. The parent sends only one message, and we actually know that we're finished with the queue when the child has received the last message. So that is fine. And does exactly what we expect it to do and destroys the queue at the correct time. Now, there is implicitly a form of coordination here because of the fact that the receive is blocking. That the child process cannot go on until it has received a message, and that counts as a mechanism of coordination, meaning that we won't accidentally destroy the queue before we have received the message from it or anything, because this is actually blocking. If we chose it not to be blocking, we would then be told actually there was no data available for us, and we would go on and we would try to print some garbage and then destroy the queue before we were done. So blocking is actually in our favor here. So let's actually run that. First we will compile it. And then run it. And as expected, we saw received 252, and Does that work as we think it should? Yes, it does. So we got a brief overview of how to work with a message queue. In particular, when we have this parent-child relationship, it's a lot easier than using the file-to-key mechanism. So we prefer that when we know we're going to have a parent and child relationship. And we can make our message, pretty much anything we want. We can have it contain other stuff if we are so inclined. Such as if we add in here m2.otherData, and then if we run it, we see what we got. So we can make our message arbitrary in length. In this case, we sent and received only one message, but that's all we needed for a brief proof of concept of how we were going to work with a message queue. Now, this only really introduces the idea of message passing as a form of inter-process communication. We will see in our next topic a very common mechanism for inter-process communication, and that is using the network. And we will see you in that next video where we start to talk about network communication.